Welcome to our discussion on Chapter 20, where we're going to be looking at electrochemistry. Electrochemistry really is just looking at the transfer of electrons in chemical reactions, and hopefully that sounds somewhat familiar to you because that is a redox reaction. And redox, remember, is just the shorthand way of saying a reduction and an oxidation reaction. So before we really get into the nitty-gritty of how electrochemistry can be measured, we need to remember a few things from Chem 1. And so we need to understand how to find an oxidation state for any element in any compound. We need to be able to write redox reactions and break them down into half reactions. From there, we can determine what's oxidized, what's reduced, what is the oxidizing agent, and what is the reducing agent. So we're going to go into all of this. I really want to make sure that we feel comfortable understanding these pieces, because if we don't understand these pieces, then the whole chapter isn't going to make a whole lot of sense. So we're going to do a bit of a review from Chem 1211. So I'm going to pull up a blank screen. And we're going to start by talking about oxidation states. Now, an oxidation state and oxidation number means the same thing. So I don't want you to think that those are two different meanings. It's the exact same thing. It's just a different way to say it. So an oxidation state tells us the charge of the atom based on how many electrons it has. And so it's really just a way of bookkeeping for us to determine how many electrons something has at the start of a reaction versus at the end of a reaction to see which way our electrons are being transferred. So we're going to look at a couple different rules that are associated with oxidation state. And the first one is that any atom in its elemental form has an oxidation state of 0. So what does that mean in its elemental form? That has to do with standard state, and we talked about standard state before. That means we're at 1 atmosphere of pressure, and we're at a temperature of 0 degrees Celsius. So for instance, hydrogen, we expect to be in the gaseous phase. So if we see H2 as a gas, then we expect it to have an oxidation state of 0. Same thing with if we just had sodium metal, for instance. So sodium as a solid, we would expect to have an oxidation number of 0. So this works for diatomic elements as well as monatomic elements. So anything in its normal elemental state has an oxidation number of 0. The next thing is looking at monatomic ions. So if we're dealing with a monatomic ion, the charge of the monatomic ion is the oxidation number, or the oxidation state. Now, oxidation states, you might recall, can either be positive or negative, and we need to specify that. So make sure that you are paying attention to if something is positive or negative, not just what its value is. So if we were to look at, for instance, let's say the nitride ion, nitride is N3-. So its charge is 3 negative, which means that its oxidation state is -3. So usually the way that we write these charges is a charge of an ion, the negative comes after the number. For an oxidation state, the negative comes before a number. If you write it either way, I won't mark it as incorrect, but I just want you to be familiar with what it looks like. And we could do the same thing with a positively charged ion. If we had strontium, that's a 2+ ion, so its oxidation state would be +2. So we have elements, we have monatomic ions, and so the next thing then is we're going to look at ionic compounds. For an ionic compound, break the ionic compound, and specifically we're going to talk about binary ionic compounds right now. Break the binary ionic compound into its ions. Oops, that should be ions. Now, what does it mean to be a binary ionic compound? Well, binary means it's just two elements. And so ionic, remember, is a metal and a nonmetal. So if we were looking at sodium chloride, we know is NaCl. So that would get broken down into Na plus and Cl minus. Well, Na plus, therefore, has an oxidation state of +1 because now it's a monatomic ion. Chloride is a -1 for the oxidation number. So we can break down an ionic compound to determine each individual atom's oxidation state by looking at what it would be if it were in the ion form. So that's for ions. Then we can look at covalent compounds. And for a covalent compound, we have a couple of rules. So I'm just going to create a little bit of a header. So for covalent compounds, we will see that the sum of the oxidation numbers must equal the overall charge of the atom, or sorry, of the compound. The sum of the oxidation numbers must equal the overall charge of the compound. And this is true for any type of compound. It's just that covalent compounds can have any charge, whereas ionic compounds are always going to be neutral. So the sum has to equal the overall charge. We're going to see that when we're trying to figure out what the oxidation numbers are, we can't just look at them in their ion form because it's not an ionic compound. However, that being said, we do have a rule, and the rule of thumb is that oxygen, when in a compound, so not just oxygen gas, but oxygen when in a compound, will have an oxidation number or an oxidation state of -2. If we know that the oxygen is -2, we can determine what the charge or what the state is of the other element in question. So let's take a look at this. For instance, polyatomic ions are considered covalent compounds because they are held together by covalent bonds since they are non-metals put together for most of them. There are some exceptions, of course, like chromate and permanganate, but generally speaking, most of the polyatomic ions are covalent compounds. So if we were looking at nitrate, for example, nitrate is NO3 with a -1 charge. So how can we figure out the oxidation numbers of each element? Well, the general rule of thumb is that oxygen is going to be a -2, straight off the bat. So we can create a mathematical equation to determine the oxidation state of the nitrogen. So recall that the sum of the oxidation numbers must equal the overall charge. How do we determine the overall charge? We look in the upper right-hand corner of our compound. So we have a -1 charge overall. So we need for our nitrogen plus our 3 oxygens. So we have 3 oxygens, each oxygen having a -2 oxidation number equals a -1. Again, we're looking for nitrogen plus our 3 oxygens, each oxygen having a -2 oxidation state. The sum of those two elements has to equal -1 since that's the overall charge of the compound. So we do a little bit of math, and we find that the oxidation number of the nitrogen has to be a positive 5. And like I said before, we could do this with elements or compounds that do not have charges. So for instance, we could look at carbon dioxide. In carbon dioxide, again, we're going to say, well, our oxygen, we know that's going to be a -2. So our equation is going to be carbon plus 2 oxygens, each oxygen having a -2 oxidation state, has to equal a sum of 0 because there's no charge written for CO2. So that makes carbon equal to a positive 4. So we have oxidation states of atoms in their elemental form, monatomic ions, binary ionic compounds, covalent compounds, and then the last one that we want to do is taking a look at ionic compounds containing polyatomic ions. So I'm going to go ahead and erase all of this because I have run out of room. So again, we're still looking at determining the oxidation state, but now we're looking at it from the aspect of an ionic compound containing a polyatomic ion. In these cases, what you want to do is start with the outer elements first and save the middle element for last. Okay, but we're going to use the same method that we just did. So let's say that we're looking at sodium chromate. Sodium chromate would be Na2CrO4. So oxygen we know is a -2. Sodium isn't going to change. It's going to be a +1. So we can set up our math equation to solve for our chromium. So we have two sodiums, each with a -1 oxidation number. Sorry, +1. I don't even know what I'm saying anymore. 2 sodiums with a +1 oxidation state, plus our chromium we don't know, plus 4 oxygens, each oxygen having a -2 oxidation state, and our overall charge is 0. So we end up with 2 plus chromium plus a -8 equals 0. So chromium plus -6 equals 0. So our chromium has to be +6. And that's how we can determine that. Now, one other trend that I want to point out to you has to do with hydrogen. So hydrogen can change its oxidation state depending on what it's with. So when hydrogen is with a metal, it has an oxidation state of -1. But when H is with a nonmetal, like in acids, it has an oxidation state of +1. So make sure that you are able to note that difference. When in doubt, use the charge from the periodic table, especially if you're dealing with something like the sodium chromate that has multiple elements in it, more than 2. So sodium is always going to be a +1 unless it's sodium metal by itself. So since that is a charge on the periodic table that is stagnant, it's never going to change, we can just automatically assume it's going to be a positive 1. So now that we have our rules of our oxidation numbers, we can go ahead and look at a reaction, determine what's being oxidized and what's being reduced, and what is the oxidizing agent or the reducing agent. So let's try that out. We're going to look at this reaction where we have magnesium oxide plus iron, and we end up making some iron 3 oxide plus some magnesium. So once this is balanced, we're going to go like this, and our equation is balanced. So the first thing that we need to do in order to determine what's being oxidized or reduced is to find our oxidation states. So go ahead and pause the video, take a second to try and figure out the oxidation state of each of these elements, and then we're going to figure out what's being oxidized and what's being reduced. So I'm going to start off looking at my magnesium oxide, and we ask ourselves, is this an element? Is it a monatomic ion? Is it a binary ionic compound, a covalent compound, or an ionic compound with a polyatomic ion? So this is a binary ionic compound, which means that we just break the compound up into its ions, and that means magnesium is going to be a +2, oxygen is going to be a -2. Then we move over to iron. Iron is in its elemental state, so it's going to have an oxidation of 0. Moving on to iron 3 oxide. Again, this is a binary ionic compound. So our iron has a +3 and our oxygen has a -2. And then lastly, our magnesium is now in its elemental form, so it is going to be 0. So now we have all of our oxidation states, and we need to figure out what's being oxidized and what's being reduced. So let's try and remember what those terms even mean. In order for something to be reduced, it is gaining electrons. And as such, that means we expect for its oxidation number as we go from the left side of the chemical equation to the right side, we expect for the oxidation state to decrease. Whereas oxidation means we are losing electrons. And so since we're losing electrons, that means that we're looking for, from left to right of our balanced equation, for an oxidation state that increases. So one really easy way to remember this, how I was taught it back in my day of school, which I know wasn't really that long ago, but I just like to say back in my day, we had something called oil rig, and that's how we remembered this. So oil is oxidation is losing, and rig is reduction is gaining. And I've heard of several other types of mnemonic devices to help remember this, so whichever one you find most beneficial is the one that you should obviously go with and use for the remainder of this chapter. But I personally like to use oil rig. So I think it's easier to start off by figuring out what is being reduced. Because for something to be reduced, it literally means it is being decreased, or it is getting smaller. So if we look at our elements from left to right in our balanced equation, which element is getting smaller in its oxidation state? And so you should recognize that magnesium is going from a +2 to 0. It is the only oxidation state that is decreasing, so this is being reduced. Then we can look for our oxidation. Again, for oxidation, we expect for the number to increase. So that has to be our iron, because it's going from 0 to +3. In this case, our oxygen stays the same. It stays at -2, which essentially just means that it is a spectator ion and it's not actually important in this reaction. It just kind of watches the redox occur. So we've determined what has been oxidized and what has been reduced. Now we're going to write half reactions. And for a half reaction, that just means that we're writing only the oxidation or only the reduction. So we're just writing half of our total reaction. So we did reduction first, so let's just do that one again. So for reduction, again, we're ignoring the oxygens. So I'm starting with 3 magnesium ions, and I'm going to be making 3 magnesium solids. Now, when we're balancing any kind of redox reaction, we not only have to be balanced based on the amount of each substance, but we have to be charge balanced as well. So over on the left side of our equation, we have 3 manganese ions, each ion with a +2 charge. So if we have 3 of a +2, that means we have an overall +6 charge on the left side of our equation. If we go to the right side of our equation, we have 3 magnesiums that don't have any charge. So overall, this is neutral or it has a 0 charge. And remember that being reduced means we are gaining electrons. So in order for us to balance out a +6 and a 0, we're going to add electrons to our equation. And since they're being gained, they're going to be in the reactant portion of our balanced equation. And so we need to add 6 electrons, which I just write as E-, in order to balance our equation. So now we have stoichiometrically balanced and charge balanced. And that's our reduction half reaction. Now let's take a look at our oxidation half reaction. So here we're starting with 2 irons and we're turning into, again, it's still 2 because we have that subscript, but now it's iron ions. So Fe3+, and we have to look at our charge. So on the left side of our equation, we don't have any charge, so that's 0. On the right side, we have a 3+, and we have 2 of it. So that gives us a 6 positive charge. So again, we need to cancel out that +6. So since this is an oxidation, we're losing electrons. So that's going to put our electrons on the right side of our equation. We're going to have 6 electrons here. Now we have our stoichiometry balanced out and we have our charges balanced out. Now, one way that you can tell that you're doing the problem correctly is if you end up with the same number of electrons in both of your half reactions. Because we can only give and take the same amount. We can't give electrons and only take 2 electrons. We have to be balanced there. So this is a really good way to check yourself. The last piece that I wanted to look at was determining if something is an oxidizing agent or a reducing agent. So we need to remember what that means. An oxidizing agent is the element or compound that is used to help something get oxidized. So an oxidizing agent, 99.9% of the time, is the substance that is getting reduced. Again, an oxidizing agent is the substance that is helping something get oxidized. And it helps that other substance get oxidized by itself becoming reduced. So the oxidizing agent and the reduced substance are the same. So in this case, what's being reduced is the magnesium oxide. So we would say, oh no, so we would say that our oxidizing agent is the magnesium oxide. And so in this case, when you're talking about the agents, you want to talk about the entire compound. And then our reducing agent is roughly the same idea. A reducing agent is a substance helping something else get reduced. And it does that by itself becoming oxidized. So we look at our equation to determine what was oxidized, and we can see that it was the iron, and it was just iron. It wasn't iron in a compound at the start of the equation. So that's our reducing agent. So we have discovered, first of all, how to write our oxidation numbers. And once we know our oxidation numbers, we can determine what's oxidized, what's reduced, how many electrons are being transferred, what the oxidizing agent and what the reducing agents are. So lots of information that we can gather just by looking at our oxidation states. So now that we have that little review, we're going to take a look at some other types of redox reactions that are a little bit more complex than what you did in Chem 1. So in 1, you did examples like we just did with the magnesium oxide and the iron, very straightforward, not a whole lot going on to them, but this is Chem 2. So we're going to take it up a notch, and we're going to look at redox reactions that are being done in solution. And particularly, we're going to break things down based on if it's in an acidic solution or a basic solution. So the first thing we're going to do is take a look at acidic solutions. And here are the steps needed in order for you to balance a reaction that is in an acidic solution. So first, we need to balance each half reaction. And the way that we find the half reactions, remember we just looked at before, is we have to determine the oxidation states so that we can figure out what's being oxidized and what's being reduced. Once we have that information, we can write the half reactions. So your first rule of thumb should always be find the oxidation states of every element in your equation. Then we can write the half reactions and balance them according to these steps. And we're going to do an example where you can see the steps occurring one by one. And once we have balanced all of that, we, again, like I said before, we need to make sure that our electrons are the same amount for what's being oxidized and what's being reduced. So here, multiply by integers if we need to make our number of electrons the same. Then we add our half reactions. And by adding half reactions, this means that we can cancel out anything that is shown on opposite sides. So we want to cancel some stuff out here. And you'll know if something should be canceled out because it'll be a reactant in one equation and product in another equation. Just like when we had intermediates in earlier chapters, it's the same idea, but these aren't really considered intermediates because this is all actually happening in one step. We're just splitting it up into several steps to make it a little bit easier. Once we have added, we just make sure that everything looks good and is balanced. So we're going to take a look at this practice problem. We're going to go through these step by step. So have these close by if you need to take a picture or whatever you need to do so that as we're working through the problem, you can see us doing step by step. So let's take a look at this equation. Right now it is not balanced, but we know that we're in acidic solution. And one way that you can determine this is we have an acid right here. This is chlorous acid. And so we're going to take a look at this reaction that's occurring in an acidic solution. And in order for us to do that, we know that we need to be balanced, because if we don't have a balanced chemical reaction, we can't really do any kind of math associated with it. So first thing you need to do is figure out the oxidation number of each atom in this equation. So again, take a second, pause the video, see if you can determine the oxidation numbers on your own, and then we'll kind of regroup and see what we can find. So the first thing I'm going to do is look at this ion, this polyatomic ion. That's a little different from ones that we had to memorize, where we have 2 sulfurs and 6 oxygens, and it has an overall charge of 2 negative. So we need to figure out our oxidation numbers. I'm going to make all of my oxidation numbers in red just to help us keep track. So we said that oxygen, when it's not by itself, and it's not by itself here, it's always going to be -2. So to figure out our sulfur, we can create our little equation. We have 2 times sulfur plus 6 oxygens, each oxygen with a -2 oxidation number is equal to a -2 overall charge. So when we do that, we should end up with a sulfur that has an overall charge of +5. So we have our +5, we have -2. That first substance is good to go. Now we can move over to our chlorous acid. This is one of those cases where we have a compound with more than 2 elements in it. So again, we're going to start by doing the outsides and then working our way in. So again, oxygen we know is going to be -2. Hydrogen here is with all nonmetals, so it's going to be a +1. So we need to find out the chlorine. So we're going to do H, which is a +1. That's what I meant to write. So 1 plus our chlorine plus 2 oxygens, each oxygen with a -2 oxidation state, equals 0. So when we do that, we see that the chlorine should be equal to an oxidation of +3. Then we move on to sulfate. Again, oxygen is -2. So to set up our equation, we're going to say S plus 4 oxygens, each oxygen with a -2 oxidation, is equal to -2 overall charge. So that means that our sulfur in this case has to be +6. And then we get to chlorine, and chlorine here is in its elemental state. It is diatomic, so it is going to be 0. Now that we have everything with its proper oxidation numbers, we need to determine what's being oxidized and what's being reduced. And then from there, we can write our half reactions. So take a look at these numbers on the top in red, and let's determine what's being reduced and what's being oxidized. So for reduced, remember we're looking for a number that decreases, and there should only ever be one. So if you have multiple substances that are decreasing, something went wrong. So the only one that is being reduced here is the chlorine. So we're going from a +3 to a 0. That's our reduced. And then for our oxidized, I'm going to choose a different color because the green is a little bit harder to see. We'll do gray. For our oxidized, again, there should only be one substance that gets oxidized, and that would be our sulfur. So we're going from a +5 to a +6. We're becoming more positive, so that's our oxidized. And a lot of the time, students at this point are saying to me, but there's only one hydrogen, so we can't even compare hydrogen on the right side. And to that I say you're correct, absolutely. However, the whole purpose here is to balance the equation. So the fact that we don't have a hydrogen on the other side just further proves that we're not balanced. So don't get hung on that and thinking, oh, well, the hydrogen must be one of the things that's oxidized or reduced. That's not the case. It'll be blatantly obvious to you. It'll be one of the elements that shows up on either side of our reaction. So now we have our oxidized and our reduced. We can write out our equations. Again, let's just start with the reduced because that's the first one that we found. And so here, for our half reactions, we want to write out as much information as we know. So we're starting with HClO2, and that's being converted into Cl2. That's the information that we have right now. So going back to our little list, we're going to start by balancing any elements other than hydrogen or oxygen. So the only element that's left in this particular case is chlorine. So we're going to put a 2 in front of the chlorous acid, and now our chlorines are balanced. The second step is to balance the oxygen atoms by adding water molecules. And we add water molecules wherever it's needed so that we're balanced. So right now, on the left side of our equation, we have 4 oxygens because we have 2 of the acid and each acid has 2 oxygens. So we have 4 oxygens that we need to balance with. So each water molecule has 1 oxygen, which means that we need 4 waters. And now we have 4 oxygens on both sides of our equation. Our next step, is to balance our hydrogen atoms. And the way we balance our hydrogen is by adding protons. Because we're in an acidic solution, we can just add protons to whatever side we need to in order for our hydrogens to balance out. So right now on the left side of our equation, we have 2 hydrogens. And on the right side of our equation, we have 4 times 2, which is 8 hydrogens. So 2 versus 8, we need 6 more hydrogens on the left side of our equation. 6 protons. Now we have 8 hydrogens and 8 hydrogens on each side. And then the last thing is to balance the charge, and we do that by adding our electrons. So we need to figure out what the overall charges are. Well, right now, on the left side of our equation, the only thing that's charged are the protons, and we have 6 of them. So we have an overall charge on the left side of the equation of +6. On the right side of the equation, we don't have anything that's charged. So our overall charge on the right side is 0. +6 on the left, 0 on the right. That means that in order to turn +6 into 0, we need to add 6 electrons. And so again, for reduction, we're always going to add our electrons to the left side. So +6 electrons. Now, everything should be balanced for our reduction half reaction. So let's take a look at our next portion in the gray, our oxidized. So we're going to do S2O6, 2-, converting into SO4, 2-. Ooh, I don't know where that extra little line came from. And so we're going to go through our steps again. Our first step was to balance elements other than hydrogen and oxygen. So that would be our sulfur. In order to balance our sulfur, we're going to put a 2 on the right side, and now we have 2 sulfurs on both sides. Then we balance oxygen by adding water. So on the left side of our equation, we have 6 oxygens. On the right side of our equation, we have 8 oxygens, 2 times 4. So 6 versus 8, we need 2 more oxygens in order to balance. So we're going to add 2 water molecules. on the left side. And now we have 8 and 8. The next step is to balance hydrogens by adding protons. And so on the left side, we have 2 times 2, so we have 4 hydrogens, versus on the right side, we don't have any hydrogens. So we're going to put our 4 protons on the right, and then we need to figure out how many electrons we need and where they're going to go. So we have an overall charge on the left side of -2, and on the right side we have an overall charge of 0. Now, how did I get 0 on the right side? Because I have 2 of a -2 charge, so that's -4, plus a +4 charge. So the -4 and the +4 cancel out, and so we have a 0 charge on the right side. We have a -2 on the left, 0 on the right, so that means that we need to add 2 electrons to the right side, and now both sides have a -2 charge. Now we can move on to our next step, which is to multiply by integers if we need to, in order for our electron counts to be the same. So we compare. In my purple equation, I have 6 electrons. In my gray equation, I have 2 electrons. So in order to turn them both into the same number, I'm going to multiply my bottom equation times 3. And that will give me 6 electrons. So my new equation is going to be 6 water plus 3 S2O6 2 minus makes 6 SO4 2 minus plus 12 hydrogens plus 6 electrons. Once we have our new equation written out, we can just cross this out because we're done with it. We don't need that information anymore. Now that we have the same number of electrons, we can add together our purple equation and our gray equation. And when we do that, we should cancel out anything that appears on both sides of the arrow. So, for example, our 6 electrons show up on different sides, right? 6 electrons on the left in the purple equation, 6 electrons in the right in the gray equation. 6 and 6, that cancels out completely. Our electrons are gone. And that's why in an overall equation, you'll never see electrons being written. So then we can look at our hydrogens, for instance, our protons. We have 6 protons in the purple. We have 12 protons in the gray. So we can cancel out 6 protons at most. So all 6 of these go away, and 6 of the 12 here go away, and we're going to have 6 left over. So that's done. Nothing to cancel out for the HClO2. Nothing to cancel out for the Cl2. So now we have water, and we can cancel out water. So we have 4 waters in the purple, 6 waters in the gray. So the most that we can cancel out is 4. So all 4 of these go away, and 4 of these 6 go away, leaving 2. So now this is all that we should have left. And we can put those together and write our final answer. So our final answer is going to be, and I'm just going to write the things from the purple and then the things from the gray. So on the reactant side from the purple, I have 2 HClO2. In the reactants from the gray, I have 2 waters. And I have 3 of this fancy ion. Makes product from the purple is chlorine My products from the gray are 6 SO4 2- and 6 protons. And that is my final answer in the black. That is the actual reaction that is occurring. And we can double check. So let's double check by counting up everything on each side. So if I start with my hydrogens, I have 2 plus 4 is 6. And I have 6 over here. Chlorines, I have 2 chlorines here, 2 chlorines here. That's good. Oxygens, I have 4 here plus 2 here. So that's 6 plus 3 times 6 is 18, right? So things are starting to get a little more hectic. So 6 plus 18, we have 24. We go over here, we have 6 times 4, that's 24. So our oxygens are balanced, and all that's left is our sulfur. We have 6 here, 6 here. Everything is balanced. This is your final answer. So what can I ask you on a test? That's probably what's going through your head right now. I could ask you in the final balanced equation, what is the coefficient of water? Or how many electrons are being transferred? Things of that nature. All right. So that's how we balance in acidic solution, which means now we're going to look at how we balance in basic solution. And this one is a little bit more complicated. And I know you're probably like, well, geez, can't be much worse than what we just did. And it's not much worse, but there is one extra step that we have to pay attention to. And so there are 2 main ways that people balance redox reactions in basic solutions. The first method is to add water instead of protons. And the second method is to balance as if you're in acid, but then at the very end, add hydroxide to get rid of the protons. That's the way that I'm going to teach, because we already looked at how to balance in an acid, so we might as well just keep doing that same pattern and just throw one more step on there. So that's what we're going to do for our basic solutions. We're going to balance like it's in acid, and then we're going to cancel out the protons by adding hydroxides. When the protons and the hydroxides come together, they form water. So let's take a look at this problem where we have some silver sulfide and chromium 3 hydroxide reacting together. And so again, you should probably notice it's not balanced. Well, yeah, that's the whole point, right? That's what we're doing. So in order for us to start balancing, we need to find our oxidation states. So take a second, try that out, see what you get. So let's take a look at what our oxidation state should be. So for silver sulfide, that is an ionic binary compound. So we just look at the charges of the ions themselves. Silver is a +1, sulfide is a -2. When we go to chromium 3 hydroxide, and this contains a polyatomic ion, so we have to be a little careful. Starting with our oxygen, because we always know what oxygen is going to be. It's a -2. The hydrogen is attached to an oxygen, which is a nonmetal. So the hydrogen is going to be a +1. And we need to figure out what the chromium is. So in order for us to figure that out, we can say that chromium plus 3 oxygens, each with a -2 oxidation, plus 3 hydrogens, each with a +1, equals 0. And so what we end up with there is our chromium is going to have a +3. Oops, that should be red. A +3 oxidation state. Then we move over to our product side. Silver is in its natural form, so it's going to be 0. Then we get to HS minus. Now we don't have any oxygens here, so how do we know what to do? Well, we know what to do because there's a hydrogen in there. So hydrogen is with a non-metal, so the hydrogen is going to be a +1. And so that means that in order for us to have an overall charge of -1, the sulfur has to be a -2. Should be red. Then we get to the chromate ion. Again, we know oxygen is going to be -2. So to find chromium, we have Cr plus 4 oxygens, each with a -2, equals -2. And so our chromium here is going to be +6. So we take all this information and we determine what's being reduced and what's being oxidized. So again, reduced means decrease. So if we figure out what's decreasing, that's going to be our silver. So silver goes from +1 to 0, it's our reduced. What's being oxidized is becoming more positive, and that's our chromium. Chromium goes from a +3 to a +6. So now we know what our half reactions are, and we can start balancing each of those individually. So let's start with our reduced, again, just to stay consistent. So we have Ag2S makes Ag plus HS minus. Now, why do I have 2 products here? Because I have to add that S in somewhere else. Hydrogens and oxygens are the only things that don't need to be present when you're writing the formulas. So the fact that I don't have a hydrogen on the left side is okay. But if I don't have silver on both sides and sulfur on both sides, that's not okay. So I have this here. Again, we're going to start by balancing anything that's not H or O. So in this case, the only thing that needs to be balanced is silver. And we're going to do that by putting a 2 there. The sulfurs are already balanced. Next, we can add waters to balance out any oxygens. Well, we don't have any oxygens, so we don't need to balance out any waters. We don't need to add any waters. Then we balance out hydrogens by adding protons. So in this case, we have 1 proton on the right side. So we're going to add a proton to the left side. Now our protons are equal. Now here's where we add in that extra step. Since this is a basic solution, what we're going to do is add a hydroxide to interact with that proton. So since we only have 1 proton, we're going to add 1 hydroxide. And anything, when we're dealing with hydroxides, anything that we do to one side, we have to do to the other side. So we add the same amount of hydroxides, 1 hydroxide. Okay. So on the left side, our hydroxide and our proton actually come together to make water. And so now we're left with a hydroxide only on our right side. So that was the added step. Add however many hydroxides you need to cancel out with the protons. And however many you add has to be added on both sides of the equation. Now we need to figure out our electron count. So on the left, we have an overall charge of 0 because water is neutral and silver sulfide is neutral. On the right side, we have silver's neutral. We have H-, that's a -1, plus hydroxide, that's another -1. So we have an overall charge of -2 on the right side. So 0 versus -2, we need to add 2 electrons over to the reactant side. So now we're going to look at our oxidized. And for our oxidized, we have the chromium hydroxide turning into chromate. So again, start by balancing anything other than hydrogen or oxygen. Chromium in this case is balanced, so we're good to go there. Then we balance our oxygens by adding waters. So on the left side, I have 3 oxygens. On the right side, I have 4 oxygens. So I need to add 1 water to my reactant side. Then we can balance hydrogens. So for my hydrogens, I have 2 hydrogens plus 3 hydrogens. So that's 5 hydrogens on the left, which means I need 5 protons. And since I've added 5 protons, that means that I need 5 hydroxides. Those will become 5 waters. And anything I add to one side, I have to add to the other side when it comes to hydroxide. And then the last step is looking at the charges. So for the charges, I have an overall charge of -5 on the left and an overall charge of -2 on the right. So to go from 5 and 2, I can add 3 electrons on the right side. Now I have a -5 charge on both sides of my equation. So we take a look at our 2 half reactions, and our number of electrons do not equal each other. We have 2 electrons versus 3 electrons. So in order for these to balance out, we need to multiply the top equation times 3, and we need to multiply the bottom equation times 2, so that we end up with 6 electrons in both equations. So our new purple equation is going to be 6 electrons plus, it's not 6, plus 3 waters plus 3 silver sulfides makes 6 silver plus 3 HS minus plus 3 hydroxides. For our gray equation, we end up with 10 hydroxide, 2 waters, 2 chromium 3 hydroxides, 2 chromates, 10 waters, and 6 electrons. So these are our new half reactions. Now we're going to do a little bit of math. Figure out what we can cancel out. So again, we can cancel out our electrons, 6 and 6. For water, we have quite a lot going on actually, because we have 3 waters here, 2 waters here, and 10 waters here. So what the heck are we supposed to do with that? Well, again, we can cancel out anything that's on opposite sides of our equation. So we can look at the 3 versus 10, and that means that all 3 of these can go away, and this 10 can now become 7. And then again, we can compare 2 and 7, get rid of this 2, and this 7 now becomes 5 waters. So our hydrogens are balanced now, which means the only thing we have left are the hydroxides. So we have 3 hydroxides versus 10. So the maximum that we can get rid of is 3. We're going to get rid of that. This 10 becomes 7. And so here's what we should have left. So let's write out our final equation. So from the purple reactants, I have 3Ag2S. From the gray reactants, I have 7 hydroxides and 2 chromium-3 hydroxides. From the purple products, I have 6 silvers, 3 HS minuses. From the gray, I have 2 chromates and 5 waters. So again, we can go through and double check, make sure that everything there looks good. So for my silvers, I have 6 versus 6. Sulfur, I have 3 versus 3. For hydroxide, it's easier if we don't think of it as hydroxide. Think of it as oxygen and hydrogen. So for my oxygens, I have 7 here, plus I have 6 here, so that gives me 13. And then if I compare with my oxygens on the right side, I have 8 here plus 5, so that's 13 on the right side. For my hydrogens, I have 7 plus 6 again is 13. For my hydrogens on the right side, I have 3 here plus 10 here. That's 13. Everything's balanced, and what we have in the black is our final answer. Now, every equation that we do is not going to be as intense as these acidic and basic solutions. For most of what we're going to do in this chapter, it's going to be the pretty straightforward ones. But you do need to be familiar with how to do this balancing, and you should expect to see something like this on the exam and the homework. So the remainder of the chapter is looking at how we can measure the voltage associated with that transfer of electrons, particularly with when we're dealing with standard solutions versus non-standard solutions, how we can determine if a redox reaction is spontaneous. All of that is coming up in the remainder of chapter 20.